Hello and welcome to Ott and Math. In this edition of Ott and Math, we're going to talk about general results for polynomial equations. And specifically what we're going to talk about is the complex conjugates theorem as it relates to the fundamental theorem of algebra, and then also coming up with polynomial equations. All right, so let's talk about our objectives for 2.7. So we want to understand and apply the fundamental theorem of algebra. We want to understand and apply the complex conjugates theorem. We want to determine the number of possible rational versus complex roots given the degree of a polynomial. And then we want to write an equation for a polynomial given a list of rational roots and a partial list of complex roots. Okay, so these are some objectives that I've already passed out to you. So let's talk about the fundamental theorem of algebra again. All right, so the fundamental theorem of algebra says the number of roots in a polynomial is equal to the highest degree exponent of the polynomial. So here's my polynomial. My highest degree exponent is 4, so I know that there are going to be 4 roots in this polynomial. They can be either complex or they can be real, but there has to be 4 roots total. So we also have said that the same value for root can be counted more than once. So if I have x minus 3 cubed, then I have x is equal to 3 as a root. It's counted 3 times. And then today we're going to talk about complex conjugates theorem and the irrational conjugates theorem as it relates to polynomials. So complex and irrational roots in polynomials always travel in pairs. So if 1 minus 2i is a root, then we know that 1 plus 2i is a root. 1 minus root 2 is a root. We know 1 plus root 2 is a root. All right, so let's talk about the complex and irrational conjugates theorem. Complex and irrational conjugates theorem says that irrational and complex roots always occur in multiples of 2. So if you have a polynomial with a highest degree of 6, so a 6th degree polynomial, then you know that there can be just complex roots. However, if you have a polynomial with a degree of 5, you know that you have to have at least one real root because the complex and irrational roots always occur in multiples of 2. So complex roots 2, another 2 leaves us with 4 possible roots out of 5 that are complex, which means that we'd have to have at least one real root. So let's see exactly what that means as we go through some problems. All right, so given a polynomial with degree as 7 listed possible combinations of rational and complex roots. So degree of the polynomial is 7. Possible outcomes are 7 real. So the number of real and complex roots have to add up to the total number of roots in the polynomial. So I have 7 total roots in the polynomial. I can have 7 real, 5 real, and 2 complex, 3 real and 4 complex, 1 real and 6 complex. I can also write this as no complex, 7 real, no complex, and I think that's what I'll do here. So let's just write this in, 7 real, 0 complex. All right, so let's take another one, 6 roots total. Figure out the possible combinations of real and complex. All right, so 6 real, no complex. We can have 4 real, 2 complex, 2 real, 4 complex, or we could have 0 real and 6 complex. All right, so remember the complex roots always travel in pairs, so that we also always have to have a multiple of 2 as some possible outcome, or 0 complex roots. So we list those out and then we write in the corresponding number of real roots. All right, let's take a couple more. 3 total roots, 1 total root. Let's figure out the possible combinations of real and complex. So we have 3 real, or 1 real and 2 complex, or we just have 1 real. Those are your answers. All right, so complex conjugates theorem, we said if you have a complex root, always has to have a conjugate. So if 7 plus I is one of the roots, then 7 minus I has to be the other root. So 7 minus I is the conjugate of 7 plus I, and 7 plus I is the conjugate of 7 minus I. The conjugate is just an extrapolation of the difference of 2 squares. The difference of 2 squares says a plus b times a minus b is equal to a squared minus b squared. And we're going to use that concept in order to determine the conjugate so that we end up with a real number result as part of the polynomial. All right, so let's see how that plays out. All right, so if 3 plus 2i is a root, then what must be the other root? So I want you to fill out these values. I'm going to pause here. All right, so if 3 plus 2i is a root, then we know its conjugate 3 minus 2i has to be a root. 2 minus root 2 is a root. 2 plus root 2 is a root. 5 plus I root 2 is a root. 5 minus I root 2 must be a root. All right, so what does that mean in terms of these being factors or roots ending up as factors in a polynomial? Well, the problem is that if 1 plus 2i is a root, then we know that 1 minus 2i is a root. And so trying to write x minus 1 plus 2i times x minus 1 minus 2i, and then finding out the resultant polynomial is going to be a rather cumbersome process, which we don't want to do. So I'm going to provide you with a rule in order to get a quadratic from two factors that are complex or irrational roots. And the rule is x squared minus the sum of the roots plus the product. And let me just put here, this is a lot of work and probably rife for potential error. All right, so the sum of the products, 1 plus 2i plus 1 minus 2i, ends up being equal to 2. 1 plus 1 is 2, 2i minus 2i is 0. So the sum of the two roots is going to be 2. So x squared minus the sum. So I have x squared minus 2x, then plus the product, 1 plus 2i times 1 minus 2i, 1 minus 2i squared. 2i squared is 4i squared. 4i squared is plus 4. So 1 plus 4 is equal to 5. And that ends up being equal to our polynomial result. So x squared minus 2x plus 5. And I'm going to say this is much easier than determining x minus 1 plus 2i times x minus 1 minus 2i. Okay, and that's the goal. All right, so here we have a couple more problems. Let's see if you can figure these out. So I'm giving you the two roots. I want you to find out if these are the two roots, what their factors would look like, and then as a result, multiplying their factors together, what the resultant polynomial or quadratic will look like. All right, so x squared minus 8x plus 13 is the first answer. X squared minus 4x plus 13 is the second answer. All right, so I didn't go through the problems. I'm expecting that you can evaluate from here. Lastly, we want to write a polynomial function given the following roots. So 3, 2 plus I. Notice that we have a missing root that I haven't given to you, right? So remember, the complex roots always travel in pairs. So 2 plus I and 2 minus I are the roots. X minus 3 produces a factor x minus 3. Or, I'm sorry, plus 3 as root produces a factor x minus 3. And then 2 plus I and 2 minus I produce the quadratic x squared minus 4x plus 5. Right, so you can figure this out by using x squared minus sum plus the product. Okay, and then we're going to multiply these two together to find our common polynomial. We're going to simplify or combine like terms, and this is the result. Right, last one, you're going to do this on your own. I'm going to pause here while you write a polynomial function giving the following roots. Okay, of course we're going to determine that the additional root is going to be 3 plus root 2. And then 3 plus root 2 and 3 minus root 2 produce a factor of x squared minus 6x plus 7. I'm going to multiply or distribute. I'm going to get these terms. I'm going to combine like terms. And we're going to end up with x cubed minus 11x squared plus 37x minus 35. All right, that's it for this edition of Otten Math. Thank you for joining. Come and join us next time when we move on to talk about Chapter 3. So we're done with Chapter 2. We talk about absolute value functions.